Welcome to this comprehensive guide on collisions and triggers in Unity 3D, designed specifically for beginners. This tutorial will walk you through the essential concepts and practical applications of these fundamental physics interactions within the Unity game engine. We'll cover everything from setting up basic scenes to writing C# scripts in Visual Studio to manage these interactions effectively. By the end of this guide, you'll have a solid understanding of how to implement both collisions and triggers to create dynamic and interactive game environments. Understanding these fundamental concepts is crucial for creating interactive and dynamic game environments. Collisions and triggers are at the heart of how objects in your game world interact with each other. Whether it's a player character bumping into a wall, a bullet hitting an enemy, or collecting an item. Mastering these mechanics will empower you to build engaging gameplay experiences and bring your game ideas to life with realistic and responsive object behaviors. Collisions detect physical contact between objects, causing them to react realistically, such as bouncing off each other or stopping movement. In contrast, triggers detect when objects overlap without any physical interaction, allowing one object to pass through another while still registering an event. This distinction is vital for various gameplay mechanics, from solid obstacles to interactive zones. We will explore both scenarios in detail, demonstrating their unique properties and applications. Let's begin by setting up a basic scene in Unity to demonstrate these principles. We'll start with a fresh Unity project to ensure everyone can follow along from the very beginning. This initial setup will involve creating some fundamental 3D objects that will serve as our test subjects for both collision and trigger interactions. This foundational step is essential for understanding how Unity's physics system works and how to prepare your game objects for interaction. First, we'll create two primary 3D objects, a cube and a sphere. These simple geometric shapes are perfect for illustrating collision and trigger concepts due to their straightforward collider properties. We'll place them within our scene, ensuring they are positioned in a way that allows for clear observation of their interactions. This step lays the groundwork for our physics experiments, providing the necessary elements for our demonstrations. For physical interactions, both objects need a rigid body component, which brings them under Unity's physics engine. Without a rigid body, objects will not respond to forces, gravity, or collisions in a physically realistic manner. Adding this component is a critical step, as it enables our cube and sphere to participate in the physics simulation, allowing them to fall, collide, and react to other physical objects in the scene. We will add a rigid body to both our cube and our sphere. Every 3D object in Unity automatically comes with a collider component, like a box collider for a cube and a sphere collider for a sphere. These default colliders are automatically attached when you create a primitive 3D object. We'll examine these components in the inspector window, noting their properties and how they define the physical boundaries of our objects. Understanding these default colliders is the first step in customizing object interaction. These colliders define the shape for physics calculations, determining how objects interact in the physical world. They are essentially invisible boundaries that Unity uses to detect when objects touch or overlap. The accuracy of these colliders directly impacts the realism of your physics interactions. We'll observe how these wireframe representations dictate the precise points of contact and how they influence the resulting physical responses between our cube and sphere. Now, let's write a script to detect collisions. We'll create a new C# script named Collision Detector within our Unity project. This script will contain the logic necessary to respond to collision events. This is a fundamental step in making our game objects interactive and allowing them to perform actions when they physically come into contact with other objects. We will then attach this script to one of our game objects. Double-click the script to open it in Visual Studio, which is Unity's integrated development environment for C# scripting. Visual Studio provides powerful tools for writing, debugging, and managing your code. Once opened, you'll see a basic script template ready for us to add our collision detection logic. This seamless integration between Unity and Visual Studio streamlines the development process, allowing for efficient script creation and modification. Inside Visual Studio, we'll implement the onCollisionEnter method. This method is a special Unity callback function that is automatically invoked when a collider or rigid body has begun touching another rigid body or collider. We will add a simple debug log statement within this method to print a message to the Unity console whenever a collision occurs, indicating which objects have collided. This will provide immediate feedback on our collision detection setup. This onCollisionEnter method is called precisely the moment two colliders make initial contact. It's a one-time event that fires at the very beginning of a collision. This is incredibly useful for triggering actions that should only happen once per collision, such as playing a sound effect, applying damage, or initiating a visual effect. Understanding the timing of this event is key to implementing precise gameplay mechanics. Beyond onCollisionEnter, we can also use onCollisionStay for continuous contact and onCollisionExit when contact is lost. OnCollisionStay is called once per physics frame for every collider or rigid body that is currently touching another rigid body or collider, useful for effects that persist during contact. OnCollisionExit is called when a collider or rigid body has stopped touching another rigid body or collider, perfect for ending effects or resetting states. These three methods provide comprehensive control over collision events. Save the script in Visual Studio and then drag it onto one of your objects in Unity, for example, the cube. Attaching the script to a game object makes it an active component of that object, allowing it to execute its logic within the game. Once attached, the script will appear in the inspector window for the selected object, confirming its successful integration. This step links our code to our game world, enabling the collision detection functionality. Run the game by pressing the play button in Unity and observe the console window as the objects collide. You will see the debug log messages we added in our script appearing in the console, confirming that our collision detection is working as expected. This real-time feedback is invaluable for debugging and verifying that your physics interactions are functioning correctly. Pay close attention to the timing and content of the log messages to understand the collision events. A helpful tip for more specific collision handling. You can check the collision.gameObject.tag or collision.gameObject.layer to identify specific objects involved in a collision. By assigning unique tags or layers to your game objects, you can create conditional logic within your onCollisionEnter method. This allows you to differentiate between various types of objects and trigger different responses based on what is collided, leading to more nuanced and complex interactions in your game. Now, let's explore triggers, which offer a different kind of interaction. Select one of your objects, like the sphere, and in its collider component, check the isTrigger box. This simple checkbox fundamentally changes how the collider behaves. Instead of causing a physical reaction, it will now act as a detection zone. Observe how the visual representation of the collider might subtly change in the scene view, indicating its new trigger status. This transforms the collider into a trigger, meaning it will no longer cause physical collisions, but will still detect overlaps. Objects will pass right through it without any physical obstruction, yet the trigger will register that an overlap has occurred. This non-physical detection is incredibly useful for a wide range of gameplay mechanics where you need to know when an object enters an area without stopping its movement, such as collecting items or entering a dialogue zone. For triggers, we use a different set of methods: onTriggerEnter, onTriggerStay, and onTriggerExit. Similar to collision methods, onTriggerEnter is called when another collider enters the trigger, onTriggerStay is called while another collider is inside the trigger, and onTriggerExit is called when another collider exits the trigger. We will add these methods to our collision detector script, each with a debug log statement to track trigger events. Notice a key difference. Trigger methods take a collider parameter, not a collision parameter, as there's no physical collision data to convey. The collider parameter refers to the collider that has entered, stayed in, or exited the trigger volume. This distinction highlights the non-physical nature of triggers, as they are solely concerned with detecting spatial overlap rather than physical forces or contact points. Understanding this parameter difference is crucial for correctly implementing trigger logic. Save the script in Visual Studio and run the game again in Unity. You'll now see trigger events logged in the console as objects overlap with the sphere, which is now configured as a trigger. As the cube passes through the sphere, you should observe onTriggerEnter, onTriggerStay, and onTriggerExit messages appearing in the console. This confirms that our trigger detection is functioning correctly, providing a clear indication of when objects enter, remain within, and exit the trigger zone. Triggers are perfect for detecting when a player enters a specific area, like a checkpoint, a pickup zone for items, or an area that initiates a dialogue sequence. For instance, when a player character walks into a trigger zone, you can program the game to automatically save their progress, add an item to their inventory, or display a narrative prompt. This allows for seamless and intuitive interactions without interrupting the player's movement or requiring explicit physical contact. When should you use collisions versus triggers? Use collisions for physical interactions, like a character hitting a wall and being stopped, a bullet impacting an enemy and causing damage, or two cars crashing. Collisions involve physical forces and responses, making them ideal for scenarios where objects should not pass through each other and their physical properties, such as mass and friction, are important. They are essential for realistic physics-based gameplay. Conversely, use triggers for non-physical detections, such as collecting items, entering a dialogue zone, or activating a trap. Triggers are perfect for situations where you need to detect an object's presence within an area without impeding its movement. For example, a player walking over a coin trigger will collect the coin without being physically stopped, or entering a pressure plate trigger might activate a nearby door without any physical resistance. This allows for more fluid and less obstructive interactions. Performance is also a significant consideration when working with colliders. Complex mesh colliders, which precisely match the shape of a detailed 3D model, can be computationally expensive, especially for collisions. This is because the physics engine has to perform more intricate calculations to determine contact points and forces. Using many complex mesh colliders in a scene can lead to performance bottlenecks, impacting your game's frame rate and overall responsiveness. A helpful tip for optimizing performance: use primitive colliders like box, sphere, or capsule whenever possible. These simpler shapes require far less computational power for physics calculations compared to mesh colliders. Even for complex objects, you can often approximate their shape with a combination of primitive colliders, significantly improving performance without sacrificing too much accuracy. This optimization technique is crucial for maintaining smooth gameplay, especially on less powerful hardware. Unity's physics layers and collision matrix allow you to control which layers of objects can interact with each other. By assigning different layers to your game objects, you can specify which layers should collide or trigger events with other layers, and which should ignore each other entirely. This powerful feature is accessed through the project settings and provides a granular level of control over your physics interactions, allowing for highly optimized and specific behaviors. This is a powerful optimization tool to prevent unnecessary collision checks. For example, you might want your player character to collide with the environment, but ignore collision checks with decorative elements. By configuring the collision matrix, you can tell Unity to skip physics calculations between certain layers, drastically reducing the number of checks the physics engine needs to perform. This leads to improved performance and more efficient resource utilization in your game. In summary, collisions are for physical interactions, requiring rigid body components on at least one of the interacting objects, and using on-collision enter, on-collision stay, and on-collision exit methods. They are designed for scenarios where objects should physically react to each other, such as bouncing, stopping, or applying forces. Remember that both objects need colliders, and at least one needs a rigid body for collision events to be detected. Triggers are for detecting overlaps without physical response by checking is trigger on a collider and using on-trigger enter, on-trigger stay, and on-trigger exit methods. They are ideal for non-physical detection zones, like collecting items or activating events, where objects should pass through each other. Triggers still require at least one of the overlapping objects to have a rigid body for the trigger events to fire correctly, even though there's no physical interaction. Mastering these concepts will significantly enhance your ability to create engaging and interactive Unity games. By understanding when and how to use collisions and triggers, you can implement a vast array of gameplay mechanics, from realistic character movement and combat systems to interactive environments and puzzle elements. These fundamental building blocks are essential for any aspiring game developer looking to create compelling and dynamic experiences in Unity. Keep experimenting with different scenarios and scripts to solidify your understanding. Try combining collisions and triggers in creative ways, and explore how different collider types and rigid body settings affect your game's physics. The more you practice, the more intuitive these concepts will become. Happy game developing, and we look forward to seeing the amazing interactive experiences you create with Unity 3D.